Hello and welcome to the first recap video in this course. In this video we're just going to go over some of the important concepts we've covered so far in the course to make sure that everyone gets them. First off, the processor in most modern computers is a piece of hardware which can execute certain operations called instructions. Typical modern processors read these instructions as binary, ones and zeros. Different processors may encode instructions in different ways, however. For example, the binary 11110100 on my particular processor represents the halt instruction, which stops all instruction execution and places the processor in a halt state. A convenient way of producing sets of instructions for the CPU to execute is by writing text abiding to a certain standard, for example the C99 standard for the C programming language, and running this text through a compiler and possibly other components including a linker and a preprocessor, to compile the text into a binary file which can be executed on a particular machine and operating system setup. If you so desire, you can inspect the binary file output from a compiler and read out the specific sequences of binary digits which correspond to particular instructions on your particular processor. You can also get a program to do this for you called a disassembler, and for your convenience you can then have these sequences of digits, these bits that make up these instructions, displayed as textual representations of the instructions. For example, the halt instruction I alluded to earlier can be expressed as the text HLT. And a set of textual representations like this can make up an assembly language, which is closely tied to the raw instructions of a particular processor. In the C programming language, we can define named chunks of code, so named sets of instructions, which we can execute at some later point. The named chunks of code are called functions, and when we want to execute the code relating to a particular function name, we do what's called calling the function. Additionally, if we define a function named main, this function will get executed first when the code is compiled and the resulting program executed. So to define this main function, we can write something like the following, where int represents the type of value that the function can give back to whatever it called, void represents that this function requires no additional values to do its job, and the curly brackets represent the section of code which we want to be related to our function name main. Most of the time when we talk about the execution of C code, we're talking about a series of statements, standalone actions to be performed, which get executed in series. Typically we have a return statement within our main function which often returns the integer value 0 to indicate successful termination of our program. An expression in C is just a piece or a fragment of code which represents a value. The plus, minus, multiply, and divide operators are commonly used in numerical expressions in C. And because expressions just represent values, we can write a return statement that returns 5 plus 2, and the expression 5 plus 2 will get evaluated to the value 7, which will then get returned as part of our return statement. We can also include other files into our source code, such as standard.io.h, a file which defines some input and output functions which have their behavior defined in the C standard. Two of the functions defined this way are Printf and Scanf, which are for writing data to the user and reading data from the user respectively. We can call a function in C, we can execute the block of code relating to a particular function name by writing the function's name, followed by a bracket enclosed, comma separated list of values that the function needs to take to do its job, called parameters, all followed by a semicolon to end the statement, to end the function call. Recall that the C language has a strict set of rules that define it, and so missing out even a single punctuation mark like a semicolon to end a line may result in an error when compiling your code. If we want to output some text to the screen using printf, we can just pass the function a series of characters to output called a string, which we denote using double quotes. Escape sequences within strings allow for the use of special characters such as new lines, for example via the \n escape sequence. Variables in C are just storage locations which can hold a particular type of value and are usually referred to by name. We can declare a variable to inform the compiler that we wish for this variable to exist by specifying the type of the variable, followed by the variable's name, followed by a semicolon to end the declaration. We can then reference the value at the variable via its name, and can assign values to the variable via the assignment operator. We can use scanf with a particular format string to read input from the user straight into a variable. You have to think about type sizes when doing this, however. On my machine, for example, the int type is only 32 bits wide, and so cannot hold values over 2,147,483,647, which may seem like a large number, but if someone wants to input 3 billion into this, it's going to break. Integer types in C, including int, short, long, and in news that may surprise you, char, can be signed or unsigned, providing a trade-off between the magnitude of values they can represent and whether they can represent negative values. Floating point fractional types such as float and double are always signed and cannot be unsigned. Continuing on the topic of variables, the section of code in which a certain name refers to a particular variable is called the scope of that variable. We can create blocks of code using curly braces, which have their own scope inside of their parent scope. One use case for this is in conditional branching, where a condition is formulated and the truth value of this condition, which boils down to 0 for false or any non-zero value, for example 1 for true, determines which block gets executed. One way of generating conditions is through comparison operators such as equals equals, exclamation mark equals, greater than and less than. And conditions can be utilized through statements such as the if statement, or more generally, chains of if, else if, and else statements, like this one here. When the program relating to this code is executed, the appropriate block will be chosen for execution depending on the conditions that are met. You can also combine the truth values of conditions using the logical and or operators, and negate values of conditions using the logical not operator. If you're familiar with Boolean algebra, these function almost exactly like logical conjunction, disjunction, and negation. Another use case for conditions is for iteration, such as in while and for loops. These repeatedly execute a block of code while a particular condition is true. For example, this code outputs the numbers from 1 to 100, separated by new lines. The loop condition is checked before the block is executed, and when its execution is finished, the condition is checked again to see whether the block should execute again. So that's all I'm going to cover in this recap video. Of course there are other things we cover, but I've tried to just go over the most important pieces in this particular video. So that is all for this time. I will see you next time to actually start learning some new material.